All right, let's call it to order, everybody. I said call it to order, not call your order. Nice try. Yes, I do parse language a little bit. All right. Well, welcome to the July version of the McKinney Amateur Radio Club meeting. Good crowd tonight. Thanks for coming. I'm going to warn you right now, we got a lot to talk about tonight. So this is, we're going to try to move things through at a pretty good clip, but just be prepared. We've got business to cover. We've got a great presentation. We've got a lot of good news to go through. So without further ado, let's get started. Let's go ahead and do the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America, to the republic which stands one nation under God, indivisible, with liberty and justice for all. All right, you guys sit down. All right, so I want to say, a welcome to all members and guests. And speaking of guests, do we have any visitors tonight? Visitors? Well, holy moly, we're not doing our jobs then. So, new call signs. Anybody get a new call sign? I know there's got to be somebody here who got an upgrade because somebody tested and upgraded at field day. So, Larry, do you want to do an intro for Mike? Microphone. Yeah. Right here is all right. Can you hear me now? Ladies and gentlemen, we have Mr. Michael Burnett, AF7KB, fasttrackham.com. He does some very good work on instruction manuals, and I can attest to his work. Highly recommend it. Contacted him, and he said he'd be glad to do a program for us. And tonight, the program is going to be on propagation. So let's have a big hand for Mr. Michael Burnett. Thanks for coming.
All right, somebody's got to stop sharing their screen so that I can share mine. And hi, everybody, and thanks for having me at your meeting. I was telling, I think your president, that we're in the midst of a big remodeling project, and I could be stuck under a sink right now, but instead I get to go to a ham club meeting, so it's a pretty good deal. Okay, let's make screen sharing happen here. That's not it. I suddenly lost the thing that would let me share screen. Maybe it's here. There we go. So there's a reason I'm showing you this highly technical desk toy. I'll just invite you, as I kind of go through the intro here, to think about that inner ring there, and what kind of equation would you write to predict what that ring is going to do next? It's a pretty simple machine. We should be able to come up with an equation for it. So just give that a little thought as we go along here. I am Michael Burnett. I am the author of the gotten to be kind of popular license training programs called the Fast Track series. And I'm also the author of this book on ham radio propagation, which is our topic today, of course. So what is propagation? Well, my take on it is propagation is everything that happens to your signal between the transmitter and the receiving antenna. Different things happen based on where the signal starts its journey, what's in the path of its journey, and what frequency the signal is. But maybe a more useful question than what is propagation would be, what is propagating? Well, radio signals consist of particles and/or they consist of waves. That's the nature of a radio signal. Now, understanding that nature, to my mind, is one of the keys to understanding propagation. Now, of course, the answer turns out to be anything but straightforward. As I said, they're dual-natured. In fact, they are so confoundingly strange that language sort of breaks down as we try to describe them. I mean, radio signals really do consist of particles or they consist of waves. But even that tortured syntax doesn't quite convey the strange duality of these things that we so casually fling out into the universe. Fair warning, this does get a little weird. We can do experiments that absolutely prove that radio signals are waves and they cannot be particles. And we can do experiments that absolutely prove that they are just the opposite. Now, before we go too much farther, just in case there are any physics professors with us here today or electronic engineers, let me say right up front, I have taken liberties with some of the physics involved in what we're addressing today in order to serve the multiple interests of time, intelligibility, and a minimum amount of calculus. So we're not going to try to resolve the dualistic nature of electromagnetic radiation here today. There's no treasure down that hole. Since we can interpret a radio signal as either a wave or a particle at our convenience, we'll use that fact to further our understanding of propagation. The good news, though, is that you're free to think of any given mode of propagation as either a wave phenomenon or a particle phenomenon, whichever makes the most sense to you for that particular mode. Now, in the book, we cover over a dozen distinct modes of propagation and several subsets of those modes, and we're not going to cover all those today because, here we are with 10,000 things to do. Instead, we'll look at a handful of modes, and along the way, we'll note whether we can apply the particle model or the wave model to better understand those modes. So we'll start down here on the ground, and we'll work our way up to the sky. Start with ground wave propagation. This one's a favorite of the top banders, the folks on 160 meters. A ground wave leaves the transmitting antenna, and at least for a while, it goes cross-country, following the curvature of the Earth. Well, how does this happen? I mean, we all learn radio waves travel in a straight line. Spoiler alert, the answer here in the real world is actually almost never. We learn early on in our radio education that radio waves travel at the speed of light, which is true as far as it goes. It's just that the speed of light isn't always the speed of light, or at least it's not always 300 million meters per second. That's the speed of light in a vacuum. In air, the speed of light and of radio waves is a little slower, and through the Earth, it's considerably slower. So to create a ground wave, we need an antenna, and a vertical is generally the superior choice here. And we need ground radials. So think of that system as inducing a wave that's partially in the air and partially in the Earth. The part of the wave passing through the Earth is moving just a bit slower than the part passing through the air. And so it moves along, and the whole thing sort of leans over and sticks close to the ground for a while. It's something like when you're riding an escalator and your hand is traveling just a little bit faster than your feet. Now, I mentioned the top banders, those folks on 160 meters, are very interested in ground waves. They can provide excellent propagation in the near range, say out to 50 miles or so. Ground wave propagation is superbly dependable. Ground waves don't fade. They don't disappear if you get a building between you and the transmitter, and they don't stop working because the sunspots are having a bad day or a bad decade. So how do we create ground waves? Well, I mentioned commercial AM stations operating down there just below our 160-meter band, spend lots of money to create strong ground waves. They do that by having massive ground radial systems under their vertical antennas. Typically, have about 120 quarter wave ground radials strung out around the base of their quarter wave vertical antenna. That is a lot of copper. And if you've bought any copper lately, you know it's a lot of money. A more economical solution for us is the inverted L antenna, with a horizontal element, a vertical element, and ground radials that are more along the lines of what most of us are accustomed to in ham radio, which means a few wires strung out wherever you could manage to string them out on the ground. Ground waves depend on ground conductivity. The more of it, the better. So if you want to create a great ground wave, you need to have the foresight to live in a part of the country with great ground conductivity. Here's a map of the U.S. ground conductivity. By the way, until rather recently, this was the official FCC map of ground conductivity that you had to use to kind of prove out the coverage area of your AM radio station. If you can read the little numbers, you'll see that Oklahoma, Kansas, your neck of the woods, and a lot of that center section of the U.S. has pretty fantastic ground conductivity. Bigger numbers is more Mohs or more Siemens of conductivity. Most of the West Coast and the East Coast, not so much. So you want to choose also the right operating frequency if you want to create ground waves. It's really unlikely you'll create much of a ground wave at frequencies above, say, 5 megahertz. And if you create one, it won't go far. So 160 meters, yeah. 80 meters, maybe. 60 meters, not totally impossible. 40 meters, really not going to happen. All right, now let's touch on VHF-UHF propagation. We must have some technicians in the house somewhere. We all learn about line-of-sight propagation when we study for our technician license. But the test never mentions the fact that down here on the ground, pure line of sight is pretty rare. Out in your area of the country, it's probably more common than where I am, but still pretty rare. I would be so bold as to say that most of the time there's no such thing as line of sight propagation. For most of us, the predominant form of propagation that we're using in the VHF and UHF bands is not line of sight, but terrestrial scatter. Our signal is being affected by goodness knows how many buildings, cars, trucks, mountains, who knows what else on the way to the receiver. Carrie and I live on the backside of a hill relative to our club's repeater. And on paper, there's no way our signal can hit that repeater. I mean, here's a plot of the topography between us and the repeater. That's the repeater down on the lower level, and that's our house up on the upper level. That is one big old hill in the way, and it's not dirt, it's basalt. So, and yet, we're on the club repeater just about every week. Carrie hosts the net at least once every 4 weeks. She used to run a weekly YL net. And so all that was done from our driveway in our truck. Our best guess is that we're either knife edge diffracting our way to the receiver over this peak right here and this one right here. Not very likely, or more likely, we're bouncing off the side of a mountain about 10 miles north of our house that does have a clear shot to our house and to the repeater. In this sort of propagation, we can think of our signal as a stream of particles, ping pong balls, ping-ponging semi-randomly around the area. Another way our VHF-UHF signals get to places beyond the line of sight is tropospheric scatter. Our atmosphere is usually not perfectly homogeneous. Think of a cup of coffee into which you just poured some cream before you stir it. That's kind of more like what the atmosphere is like. There are discontinuities in our atmosphere, and each of those discontinuities presents an opportunity for refraction. Right there is where refraction happens, at abrupt changes in density. Think of refraction as a bending of the signal's path. Bend that signal enough times, even if it's just a little each time, might get pointed back toward Earth and make it far over the horizon. Tropospheric scatter, or just troposcatter to the VHF-UHF DXers, doesn't often work in our favor, though. Typically, it's just a source of multipath. Like a terrestrial version of sporadic E, though, every now and then it opens up, much to the delight of the VHF-UHF and even microwave DXers. I think those forms of scatter are best understood with the particle model, ping-pong ball model. Now let's look at something that's probably best understood with the wave model. Now, this isn't really a propagation mode, but it's something that can, at times, rather drastically affect even a very ordinary kind of works-on-paper line-o-sight transmission, and it is called the Fresnel zone, named for this happy French fellow, Augustin Jean Fresnel. So here's a nice, clean, open path between two nice high mountains. This is one happy signal path, totally free of obstructions. Now, how often does this happen in the real world? Not often enough. Seems like there are almost always obstructions of some sort. And yet, somehow, radio communications work day in and day out. So the question is, how bad is bad when it comes to signal paths? There's actually a reasonably simple formula to model the zone between the transmitter and the receiver that needs to be fairly free of obstructions to produce a useful signal at the receiver. So that gray area there is not the transmission pattern of the antennas. That is the Fresnel zone that needs to stay reasonably clear of obstructions in order to not interfere with the signal. You can see it starts off small, and gets big, and then gets small again at the end. Now, in reality, I'm only telling you half of the story right now, but I'll get to the other half in chapter 2. Now, in this picture, that mountain we've just put in the middle is going to seriously impede the transmission, even though it's shorter than the other two. And there's a perfectly clear line o sight between the two antennas. I mean, we could stand with our binoculars right here and see this antenna perfectly well. Simply put, that mountain in the middle is going to create an interference pattern that will cancel part or even all of our signal. And we can calculate the radius of the Fresnel zone at any point along the signal path with a reasonably simple formula. It is radius equals 1/2 of the square root of lambda times distance, lambda is the wavelength, times 0.6. I'll tell you about the 0.6 in a second. So lambda is the wavelength, d is the distance from either the transmitter or the receiver, whichever is closer. Now, the rule of thumb is that 60% of the Fresnel zone radius needs to be clear at any given point. So for a practical number, that full formula would be this one, radius equals 1/2 times the square root of the wavelength times the distance times 0.6. Now, here's how this might apply in the real world. First, I do realize that you're unlikely to be calculating the Fresnel zone that extends between your car's dual-band antenna and the local repeater. That path is either going to work or it isn't. But let's say we want to build a permanent auxiliary transmitter that will send signals to a repeater up on top of a local mountain. We do a path study on one of several computer-based models that can do this sort of thing, and we end up with something like this. Everything looks great. Here's our transmitter. Here's our receiver. The only possible problem is right here. That's about 12 kilometers from the receiver. And right there, we have 20 meters of clearance over the top of that peak. What frequency do we need to use to put a solid signal up to the receiver? Wow, a social complication. Our club member, Bob, it's always Bob, has been a ham since about the time they invented lightning. And somewhere in his garage, he's pretty sure he has a perfectly fine, if slightly dusty, Heathkit 2-meter radio. While he's reluctant to part with this potentially priceless antique, his wife would be very pleased indeed if we were to loan it to the club forever for this auxiliary station. Now, should we take him up on this almost irresistible deal? Let's check the numbers. Says here, radius equals, we have a 2-meter wavelength. We have 12,000 meters from the receiver times 0.6. We need 47 meters of clearance in order to not mess up our signal. Oops, that's not going to work unless we put up a taller tower on one end or the other. Sorry about that, Mrs. Bob. Now, I have had personal and rather stressful experience with the Fresnel zone. I was working at a commercial FM station in San Diego. We were moving the studios at a rather lickety-split pace from one downtown building to another. So here's our signal path. It's from a downtown building right here up to some incredibly expensive real estate overlooking Pacific Beach and La Jolla, which is the high rent district, to say the least. Well, it turned out that we put our microwave dish up, shot our signal, we did some tests, and it was dreadful. And it made no sense because we'd been like about right here and everything worked fine. But then we just moved to here and it was not usable, the signal we were putting up there. Well, it turned out that this top of another building, this one right here, was just poking its big hairy toe into our Fresnel zone. Another section, a tower, some hasty construction, strictly to code and with all necessary permits, I assure you, and we were back in business. I told you I'd get to the other half of the story, and this is it. The interference patterns created by impingements in the Fresnel zone aren't necessarily destructive. They can also be constructive, leading to an even stronger signal. Given all the measurements, we always suspected that we hadn't managed to raise that antenna to a point that made the Fresnel zone clear, but we had just changed it enough to make the interference pattern constructive rather than destructive. In any case, it worked, and the boss didn't throw us off the top of the building, which we were pretty happy about. That gets us to what I guess is probably the big topic when it comes to propagation, and that is the ionosphere. To be an active HF operator is to have, let's say, a relationship with the ionosphere. For at least some people, it can be a pretty emotional relationship too. The ionosphere is the second highest part of Earth's atmosphere. The top layer, way up here, is the exosphere, and really, that's just the transition to deep space. There's not a lot of interest for us up here. The ionosphere starts about 30 miles or so above the ground and continues way on out to about 1,000 miles. The air is very, very thin up there. Notice we're up above the stratosphere, especially compared to down here on the Earth. It's anywhere from 100,000 times to 1,000,000 times thinner than the air that you and I are breathing. Now, in this area, 4 large, complex forces come together to create the ionosphere. They are solar radiation, the Earth's geomagnetic field, terrestrial weather, and the ionosphere's own weather patterns. Now, solar radiation. The sun is constantly bombarding us and the rest of the solar system with radiation. In the case of the ionosphere, the relevant radiation for us is the ultraviolet and X-ray frequencies. The solar wind also has its effects on the ionosphere, as well as the occasional blasts of high-energy particles that we get from solar storms. Now, this is the way we usually get taught about the Earth's magnetic field. It's nice, it's tidy. That's not how it is, though. The Earth's geomagnetic field is a constantly shifting and wobbling thing. The result, probably, don't know for sure, of what is basically a giant sloppy electrical generator at the center of the Earth. So this is a model of the geomagnetic field built by a supercomputer. As the Earth's solid iron core sloshes and rotates relative to the surrounding molten magma, electrical currents are generated. Geologists call this the geodynamo. And as we know, where there is current, there is magnetism, and in this case, magnetism tends to move around a lot. It practically ties itself in knots in some places. The magnetic lines of force also get knocked around by solar storms. All this tangling and untangling affects our ionosphere and, in the end, our propagation. Terrestrial weather can affect the ionosphere both with massive air movements, temperature changes beneath, and we think by pumping ions into the ionosphere from the tops of thunderstorms. Then there's ionospheric weather, which consists mostly of ferociously fast and strange winds. Down here on Earth, when the wind blows out of the north, the wind blows out of the north, and that's pretty much that. If a leaf gets caught in the breeze, it goes in the direction the breeze goes. You would be rather surprised if you were flying a kite and it suddenly flew into the wind. Well, things are different in the ionosphere, which consists of a form of matter called plasma. In plasma, we can have a neutral wind, an ion wind, and an electron wind, all going in different directions at the same time in the same place. Put it mildly, this rather complicates things. So we have four semi-random forces interacting in a semi-random way over vast spaces. All that does not add up to a system whose behavior is easily predicted, nor easily understood. But before we got started, I had a video playing of a desk toy, one of these deals. That is a version of a physics problem called the two-pendulum problem. It's a demonstration of chaos theory. There is no mathematical way to predict what that inner ring will do next. There never will be a mathematical way. That's what chaos theory is about, is proving that you can't predict that. Two pendulums on a cheap, simple desk toy about a foot wide. Four forces in the ionosphere over a huge area, all semi-random. Am I discouraging you about propagation forecasts at all? Because that's one thing I did come here to do. We have a giant, complicated thing, thousands of miles wide. Now, fortunately, the dominant force of all of these is the sun, and we have a reasonably good handle on its effects, at least kind of in a broad sense. So we can generate at least some modestly useful predictions, mostly with some really vintage software known as VOACAP. I'd just caution you, even if the so-called official prediction is for lousy propagation, that does not necessarily make it so. Really, propagation predictions have been almost universally, kind of like the one you see here, poor propagation predicted for over a decade now. I mean, things have just very recently started to maybe turn around. Yet, consider this. I understand the ARRL continues to send out those Century Club awards constantly. So somebody's getting some propagation. Now, what's going on up there in the ionosphere? As that ultraviolet and X-ray radiation comes bombing in from the sun, it knocks electrons in the air out of their orbits and out essentially into free space. What was a space of neutral charge has now become a space of not neutral charge. The free electron is carrying a negative charge, and the atom it left behind is carrying a positive charge. Now, for our purposes today, we're not concerned with the atom. The stuff we're interested in, the refraction of radio signals, is created by those free electrons floating around in space. The nighttime ionosphere is different from the daytime ionosphere. Of course, in reality, the ionosphere is staying more or less the same, and we're just rotating underneath it, but experientially, it changes. So the part of the ionosphere in the Earth's shadow is getting a lot less solar radiation than the part facing the sun. In fact, that whole lower part of the atmosphere on the night side doesn't have much going on in the way of free electrons at all, which turns out to be good news for us. The lowest layer is the layer we call the D layer. When Edward Appleton first started researching the ionosphere, he discovered there was a region at a fairly consistent height above ground that would return electromagnetic waves, and so he called it the E layer in his notebook for short. Later, we discovered more layers and named them the D and the F1 and F2 layers. F1 and F2 blend into one layer on the night side, and we just call that the F layer. Those layers' boundaries are constantly shifting, and they're defined by the rate of change in free electron density versus altitude, and by their behavior in regard to radio waves. Remember that picture of a glass that I showed you? When we get a rapid rate of change of electron density, that's where we get refraction. So the D layer disappears at night, leaving us for a little while around sunset and sunrise with some E layer, and as the night wears on, the F layer. Now, why is it that sometimes 20 meters works at night and sometimes it doesn't? That has to do with levels of solar activity. And the easiest indicator we have for increased solar activity, for the sun shining more brightly, is the presence of sunspots. Simply put, more sunspots equals more solar activity equals better propagation. So understand, sunspots don't create propagation. They don't do anything to propagation, really. They're just a symptom of what does create it, which is heightened solar radiation. For reasons we really do not understand, solar activity and sunspots and good HF propagation follow a 22-year cycle, giving us peaks every 11 years. Or not. Sometimes the solar maximum is a dud, like the last one. Sometimes the solar maximum doesn't show up at all, like during the Maunder minimum back around 1645 to 1715. Nobody in 1675 got their DX Century Club award. I remember. Regarding all this, nobody knows the mechanisms behind this very precisely. There are many mysteries about our ionosphere and our sun that we are quite a ways from solving. To understand what's happening to our radio signals in ionospheric propagation, I think it's useful to use our particle model of radio signals. To get a radio signal refracted, we need what you might call the Goldilocks combination of atmospheric density and solar radiation. So imagine a photon from our antenna blasting up to the ionosphere. One of three things is going to happen next. 1, your signal zaps straight through the ionosphere, never to be heard again by anyone here on Earth. 2, your signal gets refracted back to Earth, hooray. Or 3, your signal gets absorbed by the ionosphere. Let's say we're transmitting on 20 meters. For our little fantasy, that photon coming out of our antenna is 20 meters wide. It gets up to the ionosphere and encounters a bunch of free electrons that are about, say, 19 meters apart from each other. Again, this is science fiction. Bam! That signal gets bent, at least a little bit, from its straight path to outer space. It encounters a few more free electrons, spaced 19 meters apart, and then a few more, and the next thing you know, it's headed away from the charged particles and back toward Earth, where some ham thousands of miles away is anxiously listening for your signal. Now, that's a simple version of ionospheric propagation, the phenomenon that makes worldwide radio communication possible. Your signal has become what we call a sky wave, right here, as opposed to a ground wave. In practice, that sky wave might come back to Earth, bounce off the Earth, head back up to the ionosphere, get bounced again, and maybe even repeat that cycle up to 5 times before reaching that distant antenna. But what if our 20-meter photon heads up to a quiet ionosphere and finds electrons spaced 80 meters apart? Well, whoosh, probably shoots straight through. And unless you're trying to QSO with the aliens on Planet X, you're out of luck for the night. Imagine you're holding a beach ball that's 2 feet in diameter. That beach ball is your signal. You're trying to bounce it off a picket fence, maybe while blindfolded. If the fence's pickets are an inch apart, that ball's going to bounce back real dependably. But if they're 3 feet apart, it's not going to bounce back nearly as often. You'd need a 4-foot beach ball, lower frequency, to make that work dependably. So the maximum usable frequency is determined by the free electron density. As we get more free electrons, the MUF goes higher. More free electron density, or charged particles closer together, means higher frequencies will bounce instead of shooting straight through. So, obviously, 160 meters, our lowest common ham radio frequency, the one with a colossal wavelength, the biggest beach ball, must be the absolute best for skipping signals around the globe, right? 160-meter people are shaking their heads. I don't know why. Before I answer that, here's something that might at first glance seem like a distinction without a difference, but it's about to become very significant. When we bounce a signal off the ionosphere, your signal does not get reflected. It really gets absorbed and re-radiated by those free electrons. The electron is sitting there, our 20-meter signal hits it, and the electron goes, hey, extra energy. And then it releases that energy, and our signal goes its merry way. It's like we've moved our transmitting antenna to a spot a couple of 100 miles high. So why wouldn't 160 meters be the best possible DX frequency? Why do we even need the other bands? Well, there isn't just an MUF, a maximum usable frequency. There's also an LUF, the lowest usable frequency. Get below this frequency, and the signal just gets absorbed by the lower layers of the ionosphere and never gets re-radiated. How does that happen? Well, there's another mechanism at play here. So the rule is, in order to re-radiate your signal, an electron must remain a free electron, not rejoin an atom, for at least the duration of one cycle of your signal. If it finds an ion that's missing an electron and recombines before it can re-radiate the signal it just absorbed, it will join that atom and give up the energy of your signal as heat. Even if it just slams into a neutral atom, it'll give up some energy as heat. If that happens, you're not communicating, you're just warming up the atmosphere with your watts. Your beach ball's a goner. In the upper layers of the ionosphere, free electrons can last hours, even days. If they're close together, such as in the D layer, free electrons might only last a half a microsecond or so. At a microsecond, any frequency under 1 megahertz is too low and it's going to get absorbed. Since the 160 meter band starts at 1.8 megahertz, any recombination faster than about 2 microseconds is going to eat 100% of our signal. Even at a full 2 microseconds, chances are good our signal got there too late for about half of the free electrons at any given moment, because they've already been out for 1 microsecond. Of course, anything could happen with any individual free electron, but we can calculate the average rate of ionization and recombination for a given layer under given conditions. Longer waves, lower frequencies, tend to be absorbed more than shorter waves, higher frequencies. In fact, the ratio of absorption of two different frequencies can be expressed mathematically as the inverse square of the wavelength. Simply put, you double the wavelength, you get 4 times as much absorption. So let's see how this all stacks up layer by layer. In the D layer, we have lots and lots of molecules to ionize, but not much radiation to do so. Most of the radiation gets absorbed in the upper layers. Because the molecules are in close proximity, the few electrons that get free are rapidly reabsorbed. Since the MUF is determined by the amount of space between free electrons, and the D layer's free electrons have a lot of space between them, because there are not many of them, MUF for the D layer would be relatively low, making the D layer useless for VHF-UHF. Higher frequencies just shoot straight through to space. As you'll see, in the case of the D layer, MUF might as well stand for maximum unusable frequencies. At the same time, because of the proximity of those other molecules, the recombination rate in the D layer is very rapid, and that means only higher frequencies could possibly be re-radiated. Lower frequencies will be absorbed before they can get re-radiated. So in normal conditions, that means when it comes to propagation, there's no frequency high enough to get through the D layer and be refracted back to Earth by the layers above, and there's no frequency low enough to not get absorbed. So for us, almost always the D layer is a dud. Every once in a while, we get such amazing stuff happening in the E layer that will pop some sporadic E. And in that case, we can get through that D layer with that low end of the VHF band and the top end of the HF band, 10 and 6 meters, and we can get some sporadic E bounce, but that's unusual. Shortly after sunset, the D layer starts to disappear. It's when we get that cool gray line propagation. Because it's higher and it stays in the sunlight longer, the E layer persists longer than the D layer. In the E layer, the molecules have thinned out. The radiation level is higher than in the D layer. We have more free electrons, but we also still have relatively rapid recombination happening, though it's slower than in the D layer. During the day, most of the time, we can't get anything through the D layer that can be refracted by the E layer. And that adds up to 0 or very limited daytime propagation from the E layer. However, when isolated pockets of very high free electron density occur in the E layer, we have possibilities for low VHF, 10 meter, 6 meter propagation. Those frequencies can get through the D layer, and under these conditions can be refracted by those isolated pockets of high free electron density. That's what we call sporadic E propagation. Lower frequencies won't work in sporadic E because the recombination rate is still too high in the E layer, but in a sporadic E pocket, there are enough free electrons to refract a higher frequency signal. Finally, there's the F layer, the highest region of them all, up there where there's barely any atmosphere at all. Now the atmospheric density is really thinned out and the radiation is at its maximum. Lots and lots of free electrons get created, and they last a long, long time. This is why the F layer is, with just a little bit of help from solar conditions, rich territory for HF propagation. There are plenty of free electrons to refract a wide range of frequencies, and the absorption rate is very, very low. Now, the very, very good news about ionospheric propagation, if you haven't heard, is that it looks like we're getting a pretty good start on the next solar maximum. In other words, there's a chance HF, I don't want to spook it. I hesitate to even say that, but there's a chance that HF propagation is going to get better and better over the next few years. So what are the techniques to take advantage of this happy circumstance? Well, the most important technique is highly technical. You may want to take notes on this one. What you want to do is stay alive long enough for propagation to improve. It's the main thing to do. Next most important, and if you've been a ham for more than 15 minutes, you probably guess what I'm about to say, is have the right antenna. Having a jazzy new HF radio, and we have one, is all well and good, but at the risk of being skinned alive by the radio merchants, people have been communicating all over the world for a very long time with far less sophisticated radios than what's available from the merchants. Having a high-power amplifier is nice too, but unless it's hooked up to the right antenna, not a whole lot of great things are going to happen. So the object of the game, when it comes to ionospheric DX, is to get our signal to encounter lots of those long-lasting free electrons up in the F layer. So takeoff angle is very important, and generally, the lower the better. Here are 3 different takeoff angles and the resulting skywave, or lack of same. Signal A is taking off straight up. That signal encounters nothing but the minimum vertical thickness of the ionosphere, and it's on its way to a galaxy far, far away. Signal B manages a little better takeoff angle. It runs into more ionosphere on its journey. It gets diffracted some, but doesn't hang out there long enough to make it back to Earth. It's off to a different galaxy, also far, far away. Signal C takes off practically skimming the horizon, and it runs into, come back, Q. It runs into a lot of ionosphere and gets bent right back down to Earth, and now we got some DX going. So, what magic antenna, what invisible unicorn antenna do we need in order to get this nice takeoff angle? Well, one of my favorite things I ever heard about antennas is when it comes to antennas, the short answer is there's no short answer. However, I'm going to try to be brief. The main lobes of a properly installed, that's in italics, half-wave horizontal dipole will have a takeoff angle of around 35 degrees above the horizon. That's the main lobe right there. Here at 15 degrees, you're only down 3 dB. So that's going to stretch from 15 degrees to 15 degrees. Now, honestly, that's not bad at all. Even if you buy one of the commercial kits, the cost for a typical multi-band horizontal dipole is in the dozens of dollars. For those of us without any possibility of getting a dipole the proper distance in the air to achieve that, like me, which would be an honest 1/2 wavelength up, please know suboptimum can still work. fact, that's probably one of the main things that I tell people about the ham hobby is suboptimum can still work. It just won't be optimum, but optimum is optional. I strongly suspect if I went out and inspected 100 random ham stations, 99 at least would be in some significant way suboptimum. So if you want to play on the HF bands, charge ahead. Your success will depend a lot more on your persistence and the sunspot index than on whether or not you have the perfect setup. For those with the budget and the space and the commitment, sure, there's the big tower with the big beam antenna at the top. But I really want you to be clear. Those are in the nice to have list, not the need to have list. My friend who actually inspired this book and asked me to write this, I'll call him Mr. More Than 200 Countries Confirmed and 300 Worked. Yeah, he's a double DXCC, and he's never touched a radio with more than 100 watts, does have a beam antenna on a tower. But to my eye, it doesn't look like those in the picture. It's a little dinky tower. And for 40 and 80 meters, he has a long wire strung from the top of the tower. Seriously, it's a 25-footer to the top of his two-story house, certainly not the prescribed 130 feet above the ground. Still, 200 countries confirmed. He asked me to write this book. I said, John, I think you should maybe write me a book. I don't have 200 countries confirmed. Well, okay, we've gone about 45 minutes and we barely even skimmed the surface of the topic of propagation, but I hope you're walking away with at least a framework to use to think about propagation. And if you walk away with nothing else, walk away with the notion that there are literally many possible paths to successful communication, no matter what band you're on or what the time of day is. All right, I'm happy to take questions. I will switch off the screen sharing here and we'll get back to reality. Maybe stop share. There we go.
All right. Do we have any questions for Michael? By the way, great presentation, Michael. Thank you. It's very informative and well done.
And everybody left the room. Doggone it. I hate it when that happens.
Any questions for our presenter?
Comments, questions, war stories? You want to tell me you made it more than 50 miles with the ground wave? I believe you.
Hey, we had a question. We had a guy was skimming your website and saw that you had a presentation built on antennas. Are you going to turn that into a book?
Yeah.
The answer is yes, Roy.
Don't ask me when, but we just got through the cycle of doing the new general program, and for us that means we end up rewriting the books every time a new question bank comes out. I always say I'm just going to do this modularly and change out the questions that changed, but it always changes the flow. And so, yeah, so we and then we do a paperback edition, and we do an ebook edition, and we do an audio edition, and we just shipped the audio edition. So we've been working since November on getting the new general program out. So now I have a few months before the new extra comes out, and I'll be plunking away on the antenna book. It's I get a lot of requests for it, and it's taking a lot of research, and I'm having to learn some new mathematics.
There you have it, man. Math. All right. Any other questions? Yes. Okay, so Mike, the question was, we have a member here who heard that 10 watts on 20 meters will go further than 10 watts on 160 meters. If that's true, why?
You gotta throw a when in there. I mean, it's there are people who work QRP with 160 meters and work the world. It just depends on what the propagation conditions are. I guess probably on an average day, there's probably some truth to that, but it's certainly not a hard and fast rule.
Yeah, that would have been my hypothesis as well.
Yeah.
Anybody else? Well, we've got a quiet room here, Michael. I think you've satisfied most curiosity today.
All right.
Thank you so much for your time. It was really, really well done.
Well, thank you for having me, and thanks for being a ham club. It has not been an easy time for clubs. I mean, we were down to we had one meeting on Zoom only where we had 13 members show up, and we're a club of about 150 people. And so we went through some tough times there with the pandemic and everything. So thanks for hanging in, because I contend that what we do with our clubs is just a core part of the hobby and how we serve people. In my technician course, on about the first or second page, I tell people, you don't realize this right now, but one of the main reasons you're getting your license is so you can join a ham club. And I really mean it. So thanks for hanging in, and thanks for growing the way you guys seem to be growing. And again, thanks for having me as your guest. Have great nights.
All right. Have a great evening. It was hard for us to get on, especially on 15 or 40, to get on and own the station and call and do pileups. We were answering pileups. That takes more time. And we were doing more search and pounce than we were being the one doing the activator. So I think that hit it. CW, goose eggs 2 years in a row. I don't know what to say. We need some CW operators to come out and play with us for a while. That's our youngest youth. He was out there with his HT and his mama. And Dad spent a lot of time out there too. So thanks, Lewis. He should. That should be his first language, shouldn't it? Yeah. We made contacts in 80 out of 85 sections. On the back of these blue t-shirts are all the sections that are listed. We made contacts in 80 out of 85. We made contacts in every section in the U.S. except the Pacific, which is Hawaii. We could hear Hawaii. Sid was trying to get Hawaii, and they just weren't answering back. So we could hear them. We got Alaska. We got Puerto Rico. We got all the continental United States, every section. And like Texas is broke up into 3 sections. California's got a whole bunch of sections. The Northeast is weird, but we got everybody. We got 10 out of 14 Canadian sections and 4 DX, Japan, Australia, Indonesia, and New Zealand. So that was awesome. Yeah, that was awesome.
That's our new banner.
There you go. Our new club banner. That worked. We had banner facing both ways, that one and the other one. It drew people in. There were some people that were just curious. What are y'all doing? And that was great to see. Our goal was to add additional bands, so we added the third tower with 6 and 10 meters. 6 was a little, I got on 6 to begin with, and there just wasn't a whole lot going on, but we did make 6 contacts there. We made 74 contacts on 10 meters. We operated on 40, 20, 15, 10, and 6 this year. We didn't get the dipole up with the 80 and 10 or 80 and 40 meters like we had last year. So we didn't get any 80 meter contacts. Add hands-on classes. We had the hands-on class. Larry, were you able to do yours? Okay. All right. We did the 10 meter class Sunday morning, and I put together 15 kits for that class, and I came home with 3. So that was great. So there's 12 of those 10 meter dipoles out there. And I understand Robert has taken that and made a 20 meter dipole out of his and has used it successfully at a POTA already. Anybody else been able to use yours? So good deal. Good deal. On 10 meters. So cool. Good. Oh, good. Okay. Oh, wow. Get it down to yeah. To get it down under 1.5. Cool. Good. It's such a simple
antenna to make, been so effective. I had my 20 meter out recently on a POTA and hit Alaska, North Pole, Alaska. And as soon as I figured out who that was, I told everybody stand by. We're going to talk to Alaska for a while. So that was pretty cool. All right, at a satellite station, we were able to do that. Brand successfully did that. The first satellite pass occurred at 1:05. Well, the contest starts at 1. I'm sorry, the not contest starts at 1. So everybody and their dog was trying to get that first satellite pass, and that was pretty rough. He had set up for it and got it. He was able to get another satellite pass later that day, but he had an equipment failure. Those things go by so quick. You use a recorder to get go back later and get the call sign and all that. His recorder failed. Yeah, he felt pretty bad about that. Sunday morning, he was able to get that third satellite pass. And so that we needed one for the bonus point. So it's not a contest, I know, but that was great. And I think a lot of y'all enjoyed listening to his demonstration, watching that go on. Increased battery solar powered operations. We did that quite a bit last year. Andy and Jerry did 31 contacts. This year we had the 10 or the 15/40 meter station running for the majority of the time on battery solar power and made 142 contacts. I was impressed. I had a 15 amp Bioenno with a solar panel, 50-watt solar panel hooked up to it. And it ran from about 2:15 in the afternoon to about 2 or 3 in the morning, wasn't it? When we finally swapped it out. Yeah. And it was getting down to where it was starting to bounce under 12 volts. So it was ready. Then we hooked up the big old honking 50 amp hour antenna from Louis Soto. And I think that thing could still be running. So we had 2 other goals: stay safe. We only had 1 injury that I know of. How you feeling, Sid? Good. Thumbs up. That's a great thing. All right. Cause that was the injury. And we had a little bit of fun and a lot of participation. I think we had some fun. I hope everybody that wanted to could get on the air or could log or do what they wanted to do, whatever their goal was for out there. We had some other folks come by, some other members. We tried some other antennas, which was great because they worked. We had the magnetic loop antenna on FT8 for a while, running at like 15 watts, and they were making contacts like crazy. So that was great. The sun was there. It was hot. We had to hydrate quite a bit, and that's just less than optical circumstances. So we'll try real hard next year to get that the other pavilion with the more shade trees. I think that would have made a lot of difference because once you got out from under the pavilion, it was just blasting on you. So the shade trees will make a difference. Now, I am open to suggestions for next year. If somebody knows of another location that we would like to look at, let me know. And we'll take a look. We've got some time to do that. So, and you're not going to hear from me again about field day till January. So, but if you've got suggestions, I'd be glad to hear from them. Most contacted states, Ohio was number 1 by far, followed by Illinois, Florida, Michigan, even down to Texas. We had 33 contacts within Texas. USA by far was the most contacts. Canada, Puerto Rico, I know it's part of USA, and so is Alaska, but they count them separate. And then the DX contacts that we made. And who made the most contacts? Bran is our pilot master. He made 202 contacts, about 25% of the total. Dave, 107, 13%. And Klaus on FT8, 94 contacts, about 12%. David Setzer, 71 contacts. And I think this K5 INN, I think that was his, also just a typo on the call sign because that call sign doesn't exist. But Dave's not here tonight, is he? Dave Setzer? Okay. But you can find yourself up there, see how you fell in there. Even Catherine Forsett, our youth coordinator for the ARRL for this area, came by, and I looked at her and said, "Catherine, would you like to make some contacts?" And her eyes just lit up. So I kicked Kenneth off the radio. Yeah. You could have been up at 5% if I hadn't done that. But she made 4 contacts for us. So yeah. Well, I think she's down there somewhere. Yeah. Like I said, each station was occupied and being used and run, either calling CQ or searching and pouncing. It was great. Really no equipment issues to speak of. I tried to do some UPSs to keep our network running and they didn't like the heat. So we pulled them out. The network kept running. Not an issue there. FT8 was a little wonky to begin with, and that was partially my fault in getting it worked with the software for the logging software. We got that figured out and it just rocked and rolled right on in there. Some happy folks. This is early on before we're too hot. Yeah. We're still well hydrated, still happy. Yeah. Yeah. Again, there's the thanks, Lance, for the pictures. There's the aerial view, the 3 towers. Dave's already got some good suggestions to increase our 40 meters next year, maybe a 40 meter antenna up on top of one of the towers. So we're going to be looking at that. It gives you that little extra oomph to get on the frequency and own that frequency without having to battle with everybody else. Because every frequency is full and you're having to battle with everybody else, especially when the propagation is good like this year. What's that? Huh. Yeah. That's interesting. Not much of one. It was hot. The antennas were sweating. Now there's Roy. Roy said he's going to sit this girl down with me, and I guess I'll have to show her how to do it. She probably showed Roy how to do it. It was a good time. But again, look at the other 2 stations. Folks on those working. And our welcome committee. These were the first faces that visitors saw when they came to visit us. So that's a welcoming committee right there. Happy faces. And Sunday morning at field day when the sun's coming up. Not bad at all. Not bad at all. Thanks. That was good times. Again, any suggestions for next year, let us know. We'll get to start planning early, try to get the big pavilion with the trees. We could get that reserved early, even if we end up going somewhere else. The city works real well. But any suggestions, any comments, please don't hesitate to let me know. Stuff you like, stuff you didn't like. Again, air conditioning may be problematic, but other than that, I don't know. Help me get some CW operators out there. Man, those big zeros, just I don't like the internet. So maybe we can get that fixed next year. Any questions? Any comments? In the back, yes, sir. Lance has a drone, a little small drone. It's how far up there would it be? A couple 100 feet? 150 feet? Yeah. Yeah. So that's pretty cool. Any others? All right, I won't keep you any longer. Oh. A little brute strength and some rope and yeah. A little engineering. Yeah. Well, and there's a lot of experience there too from our members with a lot of experience to get that going, like this guy. All right. Thanks, Dave.
Thank you, Mike. No, it was a really great field day. I'm just going to stop. So it was good work. I had a good time this year. All right. Now can I have a motion to adjourn? Mike Blue makes the motion to adjourn. Second. Lance Chapman. All in favor, say aye. Have a great night.